A spacesuit breach turns into a race against physics. The core issue is not trauma but an interplay of pressure, gas exchange, and rapid physiological failure. The decisive variable in the last minute after a breach is the suit's ability to maintain a breathable partial pressure of oxygen while preventing lung barotrauma, ebullism, the formation of gas bubbles in bodily fluids, and rapid loss of consciousness from hypoxia or hypercapnia. The sequence of mechanical and physiological events that follows a puncture is governed by leak rate, suit architecture and backups, and human physiology under rapidly falling ambient pressure. A spacesuit is a small, mobile life support system built around three functional requirements: maintain a pressurized breathable atmosphere around the body, remove metabolic heat and carbon dioxide, and protect against micrometeoroids and the thermal extremes of space. Typical extravehicular mobility units use a low total pressure filled with nearly 100% oxygen. NASA's current EVAs use about 4.3 psi, almost equals 29.6 kPa, of pure oxygen, because lower total pressure reduces suit stiffness and improves mobility while a pure oxygen environment preserves sufficient oxygen partial pressure for respiration. The suit is layered. An inner pressure bladder provides airtight containment, a restraint layer maintains shape, and outer fabrics and armor provide thermal insulation and micrometeoroid protection. The primary life support system, PLSS, carried on the back stores oxygen, circulates atmosphere, removes CO2 via chemical scrubbers, regulates temperature through a cooling loop, and supplies power. When a breach opens, gas escapes through the hole driven by the pressure differential between suit interior and vacuum. Leak rate is a function of hole area and geometry. A millimeter-scale puncture in a multi-layer suit can produce a relatively slow leak measured in minutes, while a larger tear or catastrophic failure can cause very rapid depressurization. If the leak is slow, the PLSS and oxygen reserves can maintain adequate partial pressure long enough for the astronaut to return to the airlock or for a rescue to reach them. If the leak is fast, the sequence compresses into tens of seconds and survival depends on immediate physiological responses and the suit's emergency features. Physiologically, two processes dominate the first minute. The first is hypoxia. As ambient pressure falls, the partial pressure of oxygen available for diffusion into the lungs falls. If the suit is pure oxygen, there is a buffer because the oxygen partial pressure at 4.3 psi is higher than ambient sea level partial pressures, but a rapid drop with no time to compensate can deplete alveolar oxygen and lead to loss of consciousness. Time of useful consciousness in sudden exposure to near vacuum is on the order of 10 to 15 seconds in worst-case exposures. Exact numbers depend on the remaining oxygen, the speed of pressure loss, and prior nitrogen loading in the tissues. The second is mechanical barotrauma and ebullism. If ambient pressure falls below the vapor pressure of water at body temperature, dissolved gases and bodily fluids can vaporize in localized tissues. The most immediate danger within seconds is lung overexpansion if the lungs are not exhaled during the pressure decrease. That is why training emphasizes not holding the breath if a rapid depressurization occurs. External swelling from ebullism is often alarming but not itself instantly fatal. The primary time-critical threat is loss of oxygen delivery to the brain. Mechanical features of modern suits mitigate these effects in several ways. The PLSS contains oxygen reservoirs sized to support mission durations with a margin, and many suits include an independent emergency oxygen supply or purge mode that can provide a steady flow of oxygen at suit pressure even if primary regulators fail. Chemical CO2 scrubbers have finite capacity. A failing scrubber leads to hypercapnia, elevated CO2, which can incapacitate in minutes by causing headache, disorientation, and unconsciousness. Suits also incorporate manual isolation valves and quick disconnects that crew can actuate to stop the flow of gas through a damaged conduit, and some have localized pressure sealing features. EVA protocols add redundancy. Tethering prevents uncontrolled drift, a buddy system keeps one suited crew member close to another, and vehicles or the station airlock provide a refuge for rapid recompression. The last 60 seconds after a breach resolve is a competition between three time constants: the leak time constant, how fast suit pressure falls, the physiological time constant to unconsciousness from hypoxia/hypercapnia, and the time available from emergency systems and rescue. If the leak area is small, a typical PLSS can maintain breathable pressure for minutes to hours, buying time for crew actions, isolate the leak if possible, switch to emergency oxygen purge, and return to the airlock. If the leak is medium, crew actions focus on minimizing physiological injury, exhaling to avoid lung rupture, switching to emergency systems, and using thruster packs like safer for controlled return if untethered. If the leak is catastrophic, sudden large area failure, the time window shrinks to seconds. Immediate exhalation and recompression are essential, and survival depends on how quickly a refuge can re-establish ambient pressure. Constraints and trade-offs built into suit design define these timelines. To reduce stiffness and improve range of motion, suit pressure is intentionally lower than sea-level atmosphere, that improves mobility but reduces the pressure margin against rapid depression. To avoid decompression sickness, pre-breathing protocols remove dissolved nitrogen from body tissues before EVA so a sudden drop in ambient pressure does not produce nitrogen bubbles. However, pre-breathe procedures add operational overhead and do not eliminate all inert gas. Micrometeoroid and orbital debris shielding increases mass and decreases flexibility if made thicker. Designers must balance puncture resistance with mobility and mass limits imposed by launch vehicles and astronaut strength. PLSS size and capacity are constrained by mass and volume, limiting how much emergency oxygen and CO2 scrubbing capacity can be carried. Thermal control systems must shed metabolic heat without relying on convective cooling, and their plumbing is vulnerable to penetration. Power limits constrain active systems for leak detection and sealing. Weaknesses and edge cases are revealing. Microleaks created by tiny fragments or degraded materials may go undetected for minutes, slowly reducing pressure and causing subtle hypoxia and increasing CO2, producing cognitive impairment that can degrade the astronaut's ability to manage repairs or return to safety. Rapid micrometeoroid strikes at relative orbital velocities can impart kinetic energy sufficient to rupture multiple layers and create a catastrophic loss of pressure. Tether failure during EVA converts a breach into a retrieval problem. Propulsion packs like SAFER provide limited delta-V and are designed for station keeping, not extended rescue. CO2 removal failures create an insidious risk. With oxygen still present, CO2 retention leads to loss of consciousness over a longer time frame than a rapid vacuum exposure, and the symptoms can be misinterpreted until it is too late. Human responses complicate matters. Panic or incorrect actions, like holding the breath during decompression, can turn a survivable event fatal. Environmental context matters. An EVA in low Earth orbit near the ISS allows rapid recompression inside the station if the astronaut can reach an airlock. An excursion in deep space or on the lunar far side has no nearby refuge, and survival becomes almost entirely dependent on suit self-sufficiency. Several technological and physiological trade-offs frame current designs. Higher internal pressures reduce risk from breach and provide physiological buffering, but they increase suit stiffness, mass, and metabolic cost of moving. Mechanical counter-pressure suits, garments that press directly against the skin rather than using an internal gas pressure, promise mobility and reduce decompression sickness risk by avoiding pressurized gas, but they face launch to EVA adhesion challenges, donning complexity, uniformity of applied pressure, and local shear injuries. Active self-sealing materials and redundant bladder architectures can arrest leaks but add complexity and mass and may not react quickly enough to a large tear. CO2 scrubber technology has improved from canister-based sorbents to regenerable systems, but regenerable scrubbers require power and thermal cycles that are less useful in short, high-stress emergencies. The open engineering challenge is to shrink the critical time window following a breach without sacrificing mobility or adding prohibitive mass. Several research directions converge on that goal: materials that self-seal microscopic and mesoscopic punctures within milliseconds, distributed sensing networks embedded in the fabric to detect and localize leaks instantly, compact, high-pressure reservoirs or chemically stored oxygen that can supply a rapid partial repressurization pulse to restore safe alveolar pressures, and more advanced CO2 sorbents with very high capacity-to-mass ratios and immediate adsorption kinetics. Equally important are suit architectures that minimize single-point failures, modular bladders and redundant valves that isolate damaged sectors, and approaches that reduce physiological vulnerability, such as hybrid mechanical counter-pressure regions for the torso combined with gas-pressurized limbs. Integrating these ideas faces non-trivial constraints. Self-sealing materials must survive repeated micrometeoroid impacts and thermal cycling. Distributed sensors need to operate reliably across a wide radiation environment and not add failure modes. Rapid repressurization systems must avoid causing barotrauma from overly aggressive pressure ramps and must be lightweight and stowable. The physiological side also imposes limits. Any technology that changes breathing gas composition or pressure ramping must be validated for effects on cerebral perfusion, gas embolization risk, and long-term tissue impact after recompression. Mapping those constraints into demonstrable improvements is an active area of engineering research. Achieving a suit that can tolerate a larger spectrum of breach sizes without immediate risk will require cross-disciplinary advances, novel polymer chemistries for reversible sealing, microfluidic networks for on-site delivery of sealing agents or gases, miniaturized power systems to run smart fabrics and sensors, and updated medical protocols informed by better models of human response to partial and rapid decompression scenarios. The unresolved question is not whether incremental improvements are possible, they are, but whether a practical, field-deployable system can be realized that simultaneously reduces the last-minute window of lethality, stays within launch and operational mass/volume budgets, preserves or improves mobility, and introduces no new single-point failure modes.